Welcome back to Module 14 of Com 3073. We're going to continue our discussion of statistics in this video by talking about distributions of data, making inferences about population parameters, and calculating the confidence intervals for both averages or means and percentages. One thing I wanted to say is that if we were meeting in person, it's likely that we would have to calculate some more advanced statistics, such as chi-square, correlations, t-tests, and even analyses of variance. So you unfortunately, or maybe fortunately, aren't getting exposure to those statistics in this course. I just wanted you to keep that in mind. So let's get into the content of Module 14. For each variable you measure, it'll have an associated distribution. A distribution is the arrangement of your participants' scores on an individual variable along a continuum. And the shape of the distribution gives you important information about how the data are arrayed. The distribution you may be most familiar with is called the normal distribution, or bell curve. As you can see from the normal distribution pictured here, if you were to cut the distribution straight down the middle, both sides would be symmetrical, meaning that they're mirror images of each other. One characteristic of the normal distribution is that the mean, the median, and the mode are in exactly the same location, right down the middle. In the coming sections, we'll cover non-normal distributions. We'll discuss skewness, kurtosis, and bimodal distributions. The first quality of non-normal distributions is called skewness. Skewness refers to how asymmetrical or non-centered your data are in a distribution of scores, especially when you compare them to the normal bell curve. There are two types of non-normal distributions as they relate to skew. The first is called positive skew, where the largest concentration of data points or scores is toward the low to middle values, and the tail of the distribution, or the thin part, runs in the positive direction. The second is called negative skew, where we see exactly the opposite. The largest frequency of scores lies toward the middle to high values, and the tail of the distribution, or the thin part, runs in the negative direction. You can remember positive and negative skew by committing these images to memory through rote memorization, but the way I remember positive and negative skew was to imagine a happy or positive whale swimming toward the y-axis, and the sad or negative whale swimming away from the y-axis. Does that help? Recall what I said about distributions and measures of central tendency I mentioned a little earlier. I told you that in the normal distribution, the mean, median, and mode are located in exactly the same place, right down the middle of the distribution, because the distribution is symmetrical. This is not the case when the distribution is positively or negatively skewed. You can see from the distributions here that for skewed distributions, the mean, median, and mode are not in the middle of the distribution. You can remember each central tendency component relatively easily in skewed distributions. The mode is always easiest to spot because it's at the very top or apex of the distribution. The median is always in between the mode and the mean. So by process of elimination, you know that the mean is always nearest to the tail of the distribution. The second quality of non-normal distributions is called kurtosis. Kurtosis refers to the degree of peakedness or flatness of your distribution of scores. In reference to kurtosis, the normal bell curve is referred to as a mesokurtic distribution. There are two types of non-normal distributions as they relate to kurtosis. The first is called leptokurtic distributions, where there's a clustering of scores in one area and the tails of the distribution are really thin. The second is called platykurtic distributions, where there's no clustering of scores and the tails of the distribution are relatively thick. One rule of thumb is that all statistical packages, or even Microsoft Excel, will give you a value or measure of skewness and kurtosis. If any of these values are above plus or minus 3.0, it probably means that you have a non-normal distribution, which you will need to resolve through some type of data transformation technique. Although I want you to know that you can fix non-normal distributions through a data transformation like a log linear transformation, the specific kinds of transformations are beyond the scope of this class. The final type of non-normal distribution we're going to cover is called bimodal distribution. By its name, you probably have already guessed that this distribution has two modes or apexes in the distribution, and it looks something like this. Bimodal distributions often indicate that there are two subsamples in your overall sample that are responding consistently differently to the measure or variable. Let's move back to a broader idea of when we draw samples from populations and its implications for how we look at statistics. Let's say we wanted to know the extent to which people currently trust the media. If our population of people was all human beings on Earth, in an ideal sense, we would contact all people and ask them on a scale of, say, 1 to 100, how much trust do you currently have in media? If we were to average the responses of all 7.53 billion people on Earth, the mean would be considered a population parameter. In other words, we would have mu. But you already know that we rarely have access to entire populations, and so we need to take samples from the population and then approximate or estimate what those parameters, in this case mu, actually are. The better we do at sampling from the population, the more accurate and precise the sample mean will be to mu. But when we take samples from a population, we know that it is never going to be an exact match. This difference we naturally get between a sample statistic and the population parameter as a function of sampling is called sampling error. Sampling error acknowledges that our inferences about parameters will be biased by taking samples from the population rather than taking the entire population as a whole. Let me pose this question to you. What kinds of things do you think affect sampling error? To answer this question, you could think to yourself, what would cause more error in making an accurate prediction of the population level parameter? Let's look here at two different examples. Suppose I told you that in looking at attitudes towards media trust, one group of researchers asked just 200,000 people, whereas another group of researchers asked 900,000 people about their attitudes towards trust in media. Which sample's mean would be a better approximation of mu? If you said sample B, you'd be right. In fact, as the sample size moves towards the number of cases in the population, sampling error is reduced. Therefore, sample size is a factor that affects sampling error. Let's take a look at another example. Suppose the scores of sample A were spread out around the mean like this, and sample B's scores were spread out like this. Which pattern of dispersion would lead to a better, more precise estimate of mu? If you said sample A this time, you'd be right. A smaller standard deviation in this case would reduce the sampling error because everyone is roughly answering in the same way, giving us confidence in estimating mu. Therefore, dispersion of scores is another factor that affects sampling error. You're now probably aware that we always make imperfect estimates of the population parameter, even when we take solid representative samples from that population. As you learned, we called this level of imprecision sampling error. But how do we account for this sampling error in statistics? We include a value called standard error in the denominator of most inferential statistics. Although standard error, or you might have heard the term margin of error, varies by statistic, it usually includes two important components: dispersion in the sense of variance or standard deviation, and sample size, which we talked about earlier. The standard error of the mean in estimating mu is standard deviation over root n. I'll show you how we use standard error to build confidence intervals around x bar, or the sample average, to estimate the population average mu in the next slide. You may have heard the term confidence interval used in the past. A confidence interval is defined as a range of values of a sample statistic that's likely to contain at any given level of probability the population parameter. In most cases, we want to know whether the population parameter falls within the boundaries of the confidence interval 95% of the time, or 19 out of 20 times. Where did I come up with this arbitrary probability of 95%, which, by the way, is what we call a confidence level? It's an arbitrary threshold that Sir Ronald Fisher, one of the forefathers of statistics, came up with. He said that we should be comfortable calling something significant if we can be right about our conclusions more than 95% of the time. That also means that we can be wrong about our predictions 5% of the time, or 1 out of 20 times, and that's okay. We refer to these principles as type 1 and type 2 error, which we'll explore in the coming slides. In this example, if we set our confidence level at 95% and find the lower bound and upper bound of our confidence interval around the mean, we are saying that if we conduct the same survey or experiment over and over under the same conditions, we expect that the population level parameter, here mu, will fall within the confidence interval 95% of the time. Let me make a quick point here about type 1 and type 2 errors. For any research project you decide to do, you're going to have at least one research question or hypothesis. You're going to collect the data on that hypothesis, analyze the data, and draw a conclusion based on the results. You can do one of two things from your study. You can say that your hypothesis is unsupported, meaning that there's no significant relationship between the variables, or supported, meaning that there is a significant relationship. But there's also something happening in the backdrop of your study, and that's what's happening in reality, or at the population level. I write theoretical here to help you understand that this is often just a theoretical idea, because we will never know if any hypothesis is true or false in reality. We just don't have access to the population like this. There are four things that can happen with the interaction between your study and reality. In one case, you might conclude that your hypothesis is unsupported by the data, and in reality, your hypothesis is false. It's unfortunate that your hypothesis was unsupported, but at least you made the right decision. The other case may be where you conclude that your data support your hypothesis and your hypothesis is true in reality. This is great because you made an educated guess based on theory and you were right. Great job. But what happens when you're wrong? This is what we call error. In the case where you say your hypothesis is supported by data and in actuality it is not, we call this type 1 error. You may want to think about this as being a case of a false positive. We generally want to keep type 1 error or alpha risk low at below 5%. Then there are times when you might conclude that your hypothesis is unsupported when in reality your hypothesis is true. We call this type 2 error, although you might want to think about this as being a false negative. It's important to recognize that type 1 and type 2 error are related. When we decrease our acceptable risk of committing type 1 error, we're actually increasing our risk of committing type 2 error. In setting the confidence level, you're indicating the level of probability your population level parameter is going to fall within the bounds of your confidence interval. One interesting thing about confidence intervals is that the confidence level and the size of the interval are directly related. In other words, the lower you set your confidence level, the narrower your confidence interval will be. Likewise, the higher you set your confidence level, the wider your confidence interval will be. Remember I told you to commit the number 1.96 to memory in the previous slide, which you now know corresponds to the almighty 95% confidence level. That's because in looking at the z-table, which is based on the standard normal distribution, plus or minus 1.96 is equal to 2.5% of the scores on the top and 2.5% of the scores on the bottom of the distribution. This means that 5% of the scores lied outside of our indicated areas. That 5% that we're okay to dismiss for now. Let's take a quick look at an example problem where we might set confidence intervals around the sample average or x-bar to make our best approximation of the range mu will fall into. Before doing this, here are the standard formulas for finding the confidence intervals for means or averages at a 90% confidence level, a 95% confidence level, and a 99% confidence level. You've pretty much seen every piece of this equation before. Remember that x bar stands for the sample average, 1.96 is our z-score reflecting 95% of the sample data, and the standard deviation over root n is our standard error. Here's the sample problem. Suppose I randomly sampled a population for 100 participants to understand the average time they spent watching TV each week. Because I want to know the confidence interval for this average, in other words, the range of how much average time a person in the population will watch television, I asked each participant in the sample to estimate the number of hours per week he or she spent watching TV. I found that the average time for this sample was 23 hours with a standard deviation of 8 hours. Using the equation on the left, find the 95% confidence interval for this average. Well, to find the confidence interval, you'd have to substitute the given information into the equation. So let's start with the correct equation. The equation to find the 95% confidence interval is x bar plus or minus 1.96 times standard deviation over root n. So we know x bar, which in this example is 23 hours. We know standard deviation, which here is 8 hours, and we know n, which is 100 people. Now all you have to do is basic arithmetic. So let's start with the plus side of this equation to find the upper bound of this confidence interval. The upper bound would be 23 plus 1.96 times 8 over 10. Doing the arithmetic, the upper bound is equal to 24.57. Now let's do the minus part of this plus or minus equation to find the lower bound. It would be 23 minus 1.96 times 8 over 10, which equals 21.43. Our conclusion here would be that we expect that 95% of the time, the population mean for television viewing will fall between 21.43 hours and 24.57 hours. Means or averages are not the only thing around which we set up confidence intervals. In fact, we can set up confidence intervals around any inferential statistic so long as it makes sense. Next, we're going to talk about how to set up confidence intervals for percentages or proportions. You see listed here the standard formulas for a 90% confidence interval, a 95% confidence interval, and a 99% confidence interval. Remember that in most cases, we will be using the 95% confidence interval. The italicized p in the equation stands for the percent you find, which is in decimal form. So for a proportion like 84%, that would be written as 0.84. And n, of course, is the total sample size. When might we see a confidence interval around a percentage? Let's say, for instance, that you wanted to see how satisfied people were with the food selection on campus by asking a yes or no question, are you satisfied with the food on campus? You might want to see if the confidence interval includes anything below an arbitrarily set threshold of 50% to indicate students being less than satisfied. Or say you wanted to know who's going to win the next election for UTSA student body president between two candidates. So you calculate the 95% confidence interval for each candidate and see the degree of overlap between the confidence interval to determine whether the election will be a runaway or if it's going to be too close to call. Let's dive a little deeper into the second scenario I just referenced by looking at a real-world example. In the Democratic primary for the previous presidential election, several independent entities like ABC News and the Washington Post, Reuters, Emerson, and Harvard-Harris polled random Democrats about who they'll be voting for in the coming primary election between Joe Biden and Bernie Sanders. Immediately before the primaries, the most recent polling data showed that about 56.2% of Democrats said they'll vote for Biden, whereas 37% said they'll vote for Bernie. The question you could have answered at the time using confidence intervals is whether the Democratic primary was going to be a runaway, or was it still too close to call? If the confidence intervals didn't overlap, as shown here in red, there was some fairly strong evidence to suggest that it was going to be a runaway and Biden would be the Democratic presidential nominee, as it turned out to be. But what if the confidence intervals look like this in yellow? This would indicate that it was way too close to call. How do you know this? Remember what a confidence interval is telling us. It's saying that the population percentage is likely to fall within a certain level of confidence in the range. So it's possible that the percent of people who vote for Biden falls at the lower end of the range, whereas Bernie's percent falls at the upper end of his confidence interval. If this were the case, then Bernie would win. Therefore, overlapping confidence intervals are usually an indication that a race is too close to call. Let's calculate the confidence intervals for Joe Biden and Bernie Sanders for a hypothetical sample of 10,000 people. Here are the equations for calculating confidence intervals of proportions. For Biden, I'm going to round his percent up to 53 and use 0.53 in the equation, and of course 10,000 in place of n. Start with the calculations inside the parentheses and move outward. To calculate the plus part of this plus or minus equation for the upper bound, you multiply 1.96 by 0.005 and add 0.53. Therefore, the upper bound for Biden's confidence interval is 0.54. You do the subtraction part of the plus or minus equation to find the lower bound of 0.52. This means that in 95% of the occasions using the same sample, 52% to 54% of the people would vote for Biden. You can do the same for Bernie. This time, you would substitute 0.37 for P, or the percent of people who said that they will vote for Sanders. Following the same steps as above, you get a lower bound of 0.36 and an upper bound of 0.38. Therefore, in 95% of the occasions using the same sample, the percent of people who would vote for Sanders is 36 to 38%. The absence of overlapping confidence intervals is meaningful in that we would predict Biden to be the primary winner in a runaway election. That's all I have for Module 14. This is the extent of our discussion on statistics. Some of you may be saying to yourselves, that's it? That's what I was worried about? While others might be saying, what did my brain just get exposed to? I hope at the end you found this to be a gentle introduction to statistics. Today we focused on non-normal distributions and normal distributions. We talked about skew, kurtosis, and bimodal distributions. We then went on to talk about conceptual things as they relate to inferential statistics. Although unfortunately we could not cover calculating statistics like t-tests, chi-square tests, and ANOVAs, I hope you got some exposure to the principles of making inferences of a population parameter using sample level statistics. As always, please let me know if you have any questions about the readings or content in this video. Please don't forget to read the textbook pages listed in the syllabus, and don't forget about this module's quiz. Have a great remainder of your week, and if I don't hear from you, peace out.